So continuing with confidence intervals, we don't always construct confidence intervals around means. Sometimes we construct them around other things as well. In this case, it's going to be a population proportion. So we had talked about population proportions before. We were talking about their distributions earlier. So just a little bit of notation here. So we used P before for a population proportion. And we also will need a sample proportion. So sample proportion is new to us, one that we didn't really talk about before. But when we do a sample proportion, it's a P again, but it's a P with a hat. So this is a proportion for a sample. So the National Association of Music Merchants surveyed 800 parents of children between the ages of 5 and 18, and 632 of them said that music education had a positive effect on academic performance. So what we gather out of this is that if I'm looking for my P hat, my sample proportion, well, we had a sample of 800 people, and we just want to figure out the proportion of them who said music had a positive effect. Well, that was 632 out of that 800. Or 0.79. So 79% of the parents of children who were in an academic program said it had a positive effect. So assuming these parents would, to be a random sample, we would like to construct a confidence interval for that proportion of parents who believe that music education has a positive effect on academic performance. So we have a sample here. So just like we were doing before, what we want is we want to know what's going on with the population. So we need to find a population proportion, or try to guess where that population proportion would be, which requires us to do confidence intervals. So we need to use a point estimate. In this case, is going to be the sample proportion. And then we just add and subtract a margin of error. So we're going to talk about how we're going to find point estimate. We're going to talk about how we're going to figure out how to do that margin of error, because that's really the key to most of these confidence intervals, is just finding a margin of error. So just go through notation again. P by itself, no little special hat or anything, population proportion, and that's just for individuals in a specific category, whatever category we're looking at. So people who said music had a good impact on academic performance, that would be a special category. X is the number of individuals in the sample who are in the specified category. So those parents that said music had a good impact. And is the sample size, so all the parents that we asked. And then P hat is your sample proportion of individuals who are in a specific category. Sorry, I was trying to grab my writing tool here. And as we saw before, if I want to figure out what P hat is, then I just take the number of people who are in my category and divide it by the total sample size. Okay, so like I said, just a little notation to get out of the way. So the confidence interval. So we'd already said that that sample proportion, that was going to be a point estimate. Just like if we want to figure out a population mean, then we had to use a sample mean. We want a population proportion, then we need a sample proportion as a point estimate to give us a place to start off on. We also need a standard error of P hat. So by standard error, before this was what we considered a standard deviation. That's what we call the standard error. So we need the standard error of P hat by central limit theorem for proportions. So when we did this back in chapter 7, what we found was that if I did need that standard error, then what was going to be, that standard error, standard deviation, was going to be your population proportion times 1 minus the population proportion divided by n, and then you take a square root. So like I said, this is standard deviation of your sample proportions. So we need to compute a margin of error. So when we did a margin of error before, we need to have that critical value and that standard error multiplied together. So what we're going to use is we're going to use those z-scores that we had used before. I don't have to worry about the t-scores. We're just going to use the z-score as my critical value. And then we're going to use that standard deviation. So I multiply together to give me my margin of error. And as we said before, all I need then, if I just want to have my confidence interval, is going to be p hat plus or minus the margin of error, or p hat plus or minus the z-score times the standard error. So assumptions to be made here. The method for constructing a confidence interval for a population proportion requires that the sampling distribution to be approximately normal. The following assumptions assure this. So this is what kind of what we saw when we were talking about population proportions before. We have a simple random sample. That one's a little hard to guarantee. We kind of always assume that's what we have. The population is at least 20 times as large as the sample, so that the sampled items are independent. And the items in the population are divided into two categories. The sample must contain at least 10 individuals in each category. So if you remember what those categories were, was I take the sample size times the proportion, that had to be 10 or greater. And then we would take n, and we would take 1 times the proportion, and that also had to be greater than 10. So that's what that is telling us here, was that this is the rule that we had before. And this rule right here is basically saying the sample has to be 5% of the population, which is what we brought up when we were talking about probabilities, because that would assure that we were sampling things as if they were independent. So we don't have to worry, because remember, we're talking about proportions. Proportions are very similar to being probabilities. So a lot of those rules that went to probabilities apply to proportions. All right. So we can just guarantee some assumptions before we go ahead. All right, so going back to this problem. So a survey of 800 in a survey 800 parents, 632 said that music education has a positive effect on academic performance. So we said before, well, that means p hat is going to be 632 divided by 800, or going to be 0.79. That's my point estimate. I want to construct a 95% confidence interval for the proportion of parents who believe that music education has a positive effect. So I need the z-score for 95%, so that's z of 0.025. And this one we found a couple times. We know that's 196. So like I said, that's one of the ones that we've known. We've just been using it over and over again, so we don't actually have to look up the z-score. So that's some of my information here that I gathered. So going back to the rest of this, before I even try to do anything, I need to check my assumptions. So the things I can't really guarantee is I don't really know if this was a simple random sample. Well, earlier it said it was a simple random sample, but we kind of assume that. I don't actually know what the real size of all the parents is, but we're going to assume that 800 is 5%. So the assumption that we do test is just really this part of the assumption. This is the one part we actually can test. The rest of it is kind of assumed that it's given to us. So we have, in our case, it's going to be our p hat because we don't have p. I'm trying to get my calculator to come up. My sample size is 800. So I have 800 that's my n, times my p hat, which is 0.79. Which is going to be 609, which is definitely greater than or equal to 10. So we're okay here. Yay, that's good. The other part is we need to take 800 and then multiply it by 1 minus 0.97. I thought that number didn't seem right. I thought it should be 6. I put in a typo. It was actually this, which makes sense. I was wondering what went wrong there. I accidentally put in 0.76. So if I do 8 times 1 minus 0.79, that's going to leave me with 168. That's greater than 10. So this is how many people were saying it had a positive effect. This is how many people were not saying it had a positive effect. So that's what we're looking for, is we're looking for the people who favor and the people who don't. So we're looking at basically at the event and its conjugate. And we're just going to see, make sure that the portion of the population in either case is going to be greater than 10. So my assumptions check out. So that means that I can do the rest of this. So as we said, we know our point estimate, that's given to us. Because we're only using z-scores, as we said before, the z-score for 95%, quick reminder, if I take 95% out of the center, that leaves 5% that's left over, and 2.5% goes in each tail. And as a decimal, that's going to be 0.025. So we need a z-score of 0.025. So if you want your z-tables, you went to the charts we had, anything we had, but we should get is that z-score is going to be 1.96. So the other thing that I need is I'm going to need, I'll do this, is I'm going to need the standard error. And standard error, if you remember, is going to be the square root of p times 1 minus p, or sorry, p hat, 1 minus p hat divided by n. Well, p hat is 0.79, and then we have 1 minus 0.79, and that's going to be all divided by 800. Okay, so 0.79 times 1 minus 0.79 divided by 800. And if I take the square root of all of that, that is going to give me approximately 0.0144. So round out that far. All right, so my margin of error, as always, is going to be the z-score times your standard error. Like I said, not much has changed here compared to everything else. It's just there's that little change about how we find that standard error. We got a z-score of 1.96, and we are going to multiply that to 0.0144. And that's going to give us 0.028224. So that's my margin of error. So if I want to have my confidence interval, my 95% confidence interval, for my population proportion is going to be my point estimate of 0.79 plus or minus my margin of error, so plus or minus 0.028224, or 0.79 minus If we subtract, that's going to give me an interval that goes between we're going to go to 0.761776 less than or equal to your P, because we're looking for a population proportion. And then on the other side, it's going to be less than 0.818224. So what we expect is that we're 95% confident that the population proportion of parents who believe that music education had a positive effect is somewhere between roughly 76% and 82%. All right, do this one more time. Well, two more times actually. In 2023, there were 3,595,818 births in the United States. The month with the most births is August with 322,359. We want to construct a 90% confidence interval for the proportion of births in August. Okay. So a couple things we need to do here is we need to test our assumptions. Before we can even test those assumptions, I know what N is. I know it's my total number of births in the United States in 2023. What I need to figure out is what is my sample proportion. Well, so we're looking for the proportion of births in August, and we have the number of births in August. So I just need to take the number of births in August and divide by the total number of births. Okay, second. 233, 359, 3595, 818. So what we get here is we get approximately 0.0896 5. Let's just round out a little further because we're doing a bunch of rounding. Let's get our answers a little closer. So round out that far. Okay. And usually we expect is because there's 12 months. Like I said, this is a little higher than what would be normally expected because what we expect is actually 8.3%, and we got almost 9% here. Okay. The next part of this, like I said, is we're just going to test those assumptions now. So this first part, we really don't need to do the calculation on, because if we have n times p hat, what I should get back is how many births I had. We saw that earlier. So n times p hat should be the 3,220,000. Sorry, I got off track there. 359 births. This is definitely greater than 10. So n1 minus p hat. So that would be pretty much all my births that are left over. But that would be the 3,595,818 times 1 minus 0.08965. 359,518. Okay, and that's going to give us approximately, because there's a little bit of rounding going on. I'm still at 3 million births because most of them are going to be in here. So roughly about somewhere around there. And that's definitely greater than 10. So our assumptions check out. We should basically have a normal distribution. Everything that I'm finding with my really what it is coming down to is my standard deviation is going to make sense when I start to figure it out, because everything fits with central limit theorem. So this is going to be a normal distribution. All right, so before we do anything, we need to figure out what a 90% confidence interval again is. So we're just going to quickly go through that again. So just a quick review with the calculator, what we're doing here. So we got a 90% confidence interval, meaning 90% is exactly in the center here. So when we find alpha, alpha is 1 minus my 0.9 or is 0.1. So we have 0.1 left over. So if I divide that by 2, I have 0.05. So basically we're saying we have 5% left over for each tail. So we are looking for Z of 0.05. So we have an area. So remember, this is kind of going generic for everybody's calculator. We're going to go second bars. And we're doing number 3 because we're inverting our normal curve. And we put in that area first. So we keep doing to the left because that is what almost everybody's TI-84 can handle, is doing that area to the left. So we're just going to make sure that it stays that way. So we do area to the left. And we get a negative 1.644, or 45 is really what it is. So what we did was we found this z-score because we're looking to the area to the left of it, which is 5%. But we want this positive z-score, so all that is we just changed that from a positive from a negative to a positive. So like I said, just a quick reminder of how we do that. But that is what my z-score is going to be. That is my critical value. All right, so to figure out that confidence interval, we have our point estimate, we have our critical value, we just need to have our standard error. And once again, that standard error is going to be the square root of my p hat times 1 minus my p hat divided by the sample size. So this is going to be big, so I'm going to give us a little bit of space here. So we know on the bottom, my sample size is 3,595,818. And on top, we're going to have 0.08965 times 1 minus 0.08965. Shoot, lost out my calculator, so let me do that one more time. 8,965 times 1 minus 0.08965 divided by 3,595,818. And we do the square root. This is going to be a very small standard error, or partly because that bottom is so huge. But we're going to end up with a 0.00015. So we'll go out that far. So that matches with this then. All right. So that confidence interval for births, 95% confidence interval for the portion of births in August. And this one is not going to have a lot of wiggle room to it. It is going to be 0.08965 plus or minus. So we need that z-score of 1.645 times 0.00015, or 0.08965 plus or minus 1.645 times 0.0065. Oops, missing a 0.065, which is going to be 0.12325. All right. So if we add and subtract that margin of error, we're going to get, let me make a little space down here, get rid of something. Where we're expecting that population proportion to be. So we're looking for P, remember? P is going to be in between 0.08965 minus 0.00025. So 0.08940 is what it's going to be. And then if we add it, it's 0.08990. So what we're seeing here is basically because like I said, we're looking at all August births. Our sample is just really just 1 year. So technically, we probably shouldn't have done this because it's not really a simple random sample at that point. But it is a sample that is just 1 year, but it's telling me that what I'm expecting probably any year is I'm going to have somewhere between 8.94 and 8.99% of all births are going to be in August. Okay, so we're going to put a little more application to what we're doing here. All right, so a simple random sample of 200 third graders at a large school district was chosen to participate in an after-school program to improve reading skills. After completing the program, the children were tested, and 142 of them showed improvement in reading skills. So first part is we want to attest the assumption that we have a normal distribution of proportions. So n times p. Well, we have 200 fifth graders, even if I figure out that proportion, that's what n times p is going to be. It's going to be 142, which is greater than 10. Then when we find n of 1 minus p, that's really just like what's left over. So we had 200 people. We take out 142 of them, and that is going to leave us with 58, which is also greater than 10. So assumption checks out. I said, you can go find your proportions, but that's what we're looking for. So n times the proportion should give me what the proportion that we were looking for originally, which is that 142. And if I figure out what p is, actually p hat. And then the other part of it is just what's left over. Because like I said, n times p and n times 1 minus p, they're complements. So one is the event happens, the one is the event doesn't happen. All right, so if we want to figure out that confidence interval, we have a lot of the information already. So p hat, that is going to be 142 divided by 200. And that is going to be 0.71. Then we know that the z-score, so we have 95% again, or 95% confidence interval. So we're going to stretch a 95% confidence interval for the proportion of third graders in the school districts whose reading scores were improved after the completion of the program. Well, we already know that one. That z-score is always 1.96 for 95%. My standard error, that's going to be the square root of 1.71 times 1 minus 0.71 divided by my sample size of 200. 71 times 1 minus 0.71 divided by 200. That is going to give me roughly 0.0, let's go 32. Okay, so if I make that confidence interval, well, let's first find margin of error. Margin of error is going to be the z-score, the 1.96, times the standard error of 0.032. So that margin of error is going to be 0.063 if we round it to the way we've been rounding. So my 95% confidence interval is going to be, my point estimate is 0.71 plus or minus my margin of error of 0.063. So my population proportion is going to be between 0.71 times 0.063, between 0.647 and 0.773. So we're 95% confident this is going to happen, right? Well, that means really what it's telling me is that when each time I collect a sample, so this is my distribution of sample proportions. So my p hats, we expect to be normal because the assumptions were verified. And we know that 95% should be between 0.647 and 0.773. So this last question here is this. Is it reasonable to conclude that 60% of students would improve their reading score exams after completing the program? More than 60%. So 60% would be here. So would it be reasonable to conclude that more than 60% of students would show an improvement in the reading scores after completing the program? Well, we would have to probably say, yeah, because we at least know 95% do. So over 95% of samples should show of samples should have 60% or more of the population. I got lost my there. Over 95% of the sample should have 60% or more of the sample showing improvement. It's kind of a little sloppy writing there. That's kind of really what we do when we're kind of figuring out these confidence intervals, is they also kind of, they softly tell us probabilities of events in a way. Because remember, I'm not telling you what's the probability of capturing the population mean. It's really telling me how many sample proportions should be in a certain area. Therefore, it's telling me kind of like, giving me an idea of likelihood. So I'm constructing something that says that 95% of my sample proportions are are going to have roughly about 64.7% or 77.3% of students showing an improvement in reading, which means that over 95% of samples should show that 60% or more students are showing improvement. Like I said, because 60% is right here. So there's only this little bit in the tail that's not showing any improvement, and this is all the people showing improvement. So it's highly likely that yes, they would be. So the short answer is, so yes.